Alright, so this is my idea of a good title for this video. Probably video series, since this is quite a long article. And they say here, before diving deeper into how Windows manipulates and validates a shadow stack, the shadow stack for threads, there are two parts of its implementation that must first be understood. So the first is the actual location and permissions of the SSP. So the two parts to be understood would be permissions and the store-restore. This mechanism used to store-restore the SSP when context switching between threads, as well as how modifications can be done to SSP when needed, such as during exception unwinding. To explain these mechanisms, we'll have to delve into an Intel CPU feature that was originally introduced by Intel in order to support Advanced Vector Extensions, AVX instructions, and first supported by Microsoft in Windows 7. And since adding support for this feature required a massive restructuring of the context structure into an undocumented context_ex structure, and the addition of documented and native APIs to manipulate it, we'll have to talk about the internals of that too. Alright, so that's what I have for notes on that paragraph. Finally, we'll have to go through some compiler and PE file format internals, as well as new process information classes to cover additional subtleties and requirements for CET functionality on Windows. We hope the table of contents below will help you navigate this thorough coverage of these capabilities. Additionally, when relevant annotated source code for the various newly introduced functions is available by clicking the function's name based off our associated GitHub repository. So I'll take this link and put it in our notes here. Alright, so we're going to scroll past the table of contents and start here at X state internals. The x86-64 architecture class processors originally began with a simple set of registers which most security researchers are familiar with. We have our general purpose registers, RAX, RCX, your control registers, RIP, RSP, for example, floating point registers, XMM, YMM, ZMM, and some control, debug, and test registers. As more processor capabilities were added, however, new registers had to be defined, as well as specific processor state associated with these capabilities. And since many of these features are local to a thread, they must be saved and restored during context switches. This is some intense documentation. Wait a minute, it's just the entire manual. Here we are. It is the responsibility of the SMI handler code to properly preserve the state of information. Therefore, the SMI handler must follow the rules described in Chapter 13. Anyways, in response, Intel defined this, which associates various processor states with bits in a state mask, and introduces instructions such as xsave and xrestore, get it? To read and write the requested states from an xsave area. Since this area is now a critical piece of CET register storage for each thread, and most people have largely been ignoring xsave support due to its original focus on floating point, AVX and memory protection extensions, MPX features, we thought an overview of the functionality and memory layout would be helpful to readers. So xsave area. As mentioned, the xsave area was originally used to store some of the new floating point functionality like AVX that had been added to processors by Intel, and to consolidate the existing x87 FPU and SSE states that were previously stored through the fxstore and fxrestore instructions. These first two legacy states were defined as part of the legacy xsave area, and any further processor registers, such as AVX, were added to an extended xsave area. In between an xsave area, header is used to describe which extended features are present through a state mask called xstate_bv. At the same time, a new extended control register, XCR0, was added, which defines which states were supported by the operating system as part of the xsave functionality, and the xgetBV and xsetBV instructions were added to configure XCRO and potentially future XCRs as well. For example, operating systems can choose to program XCR0 not to contain the feature state bits for x87 FPU and SSE, meaning that they will save this information manually with legacy FX store instructions and only store extended feature state in their Xsave areas. So as the number of advanced register sets and capabilities, such as memory protection keys, which added a protection key register user state, grew, so as these capabilities grew, newer processors introduced a distinction between supervisor state that can be only modified by CPL0 code using Xsaves and X restores, as well as compaction and optimization versions. And they add on here to complicate matters in Intel type fashion. So I hope I understood that paragraph correctly. Give me an example of an advanced register set. And so I jumped ahead with my next question. What is the model specific register called? Apparently this is new, called IA32_XSS, and it was added to define which states are supervisor only. Okay, so we have not compacted and optimized. Here's the legacy area. Here's the header area. Xsave area in optimized versus not optimized formats in a thread where AVX and CETU are not enabled and IPT and PKRU are enabled but were not used since the last context switch. Should have wrote this down in my notes. Okay, so PKRU, protection key register user state. They go on to say the optimized Xsave mechanism exists to ensure that the only processor state which has actually been modified by another thread since the last context switch, if any, will actually be written in the Xsave area. Alright, in internal processor register, XI or X in use exists to track this information. When Xsave opt is used, the Xstate BV mask now includes only the bits corresponding to states which were actually saved and not simply that of all the states requested. Xsave mechanism, on the other hand, fixed a wasteful flaw in the Xstate design, as more and more extended features were added, such as AVX 512 and Intel processor trace. It meant that, even for threads which did not use these capabilities, a sufficiently large Xsave area needed to be allocated and written into, full of zeros, needed to be allocated and written into by the processor. While optimized Xsave would avoid these writes, it still meant that any extended features following large yet unused states would be at large offsets away from the base Xsave area buffer. Super fascinating, and I hope me reading this out loud helps you guys as much as it helps me. Let's finish up this section, and then I will make a separate video. With Xsave C, this problem is solved by only using space to save the Xstate features that are actually enabled and in use, as compaction implies optimization. By the current thread and sequentially laying out each saved state in memory, without gaps in between, but potentially with a fixed 64-byte alignment, which is provided as part of an alignment mask through CPUID. The Xsave area header shown earlier is now extended with a second state mask called XCompBV, which indicates which of the requested state bits that were requested might be present in the compacted area. Note that unlike XStateBV, this mask does not omit the state bits that were not part of X in use. It includes all possible bits that could have been compacted. One must still check XStateBV to determine which state areas are actually present. Finally, bit 63 is always set in XCompBV when the compacted instruction was used as an indicator for which format the Xsave area has. So bit 63 and a 64-bit number. Thus, using the compacted versus non-compacted format determines the internal layout and size of the Xsave area. Alright, so I added these two questions. They say, thus, using the compacted versus non-compacted format determines the internal layout and size of the Xsave area. The compacted format will only allocate memory in the Xsave area for processor features used by the thread, while the non-compacted one will allocate memory for all the processor features supported by the processor. So all the features. If we're using non-compacted, though, This format will only populate the ones used by the thread. The diagram below shows an example of how the Xsave area will look like for the same thread, but when using one versus the other format. That's a pretty good visual. Now I just wanted to go up here and look at this one again. This wording, optimized versus not optimized and compacted versus not compacted, is tripping me up. But lucky for me, they have a nice little summary here. We could use that to wrap up this video. So which states the Xsave or Xrestore family of instructions will work is a combination of one of four things. One, what state bits the OS claims it supports in XCRO. What state bits the caller stores in EDX EAX when using the Xsave instruction. Intel calls this the instruction mask. Okay, I kind of like that information saved as a note here. If using the non-privileged instructions, which state bits are not set in EA32. Alright, so what are we reading? The states of this family of instructions will depend on if using the non-privileged instructions. That makes sense. Our last one. On processors that support optimized Xsave, which state bits are set to or set in X in use? It's an internal register that tracks the actual X state related registers that have been used by the current thread since the last transition. Okay, so I summarized those four by writing in my notes like this, and for you B-type personalities, you're probably dying inside because I did not use capital letters, but whatever, too late now. Once these bits are masked together, the final set of resulting state bits are written by the Xsave instruction into the header of the Xsave area in a field called the Xstate BV. In the case where compacted Xsave is used, the resulting state bits, omitting bullet 4, are written into the header of the Xsave area in the XComp BV field. The diagram below shows the resulting masks. So we'll end with this pretty picture. In the next video, I'll talk about Xstate configuration.